Okay, hello, this is Dr. Muhammad, and this is another video under design of steel structures according to AISC. Today we are going to start with beam column, and we are going to have these contents for today. I'm going to give an introduction to beam column, and then I'm going to talk about the interaction formula, and then I'm going to give an example and wrap up after that. Okay, let's go to the introduction directly and see how we can understand the meaning of beam column. In general, when we are talking about frames where that we have different elements like columns and beams, generally we are like thinking about the vertical columns here to carry only axial loads. So we are under this perception that is vertical elements or the columns, they are going to carry only vertical load or axial force. And for beams, we are expecting that they are having flexural straining actions under the lateral loads that is being applied on their axis. But when we face, actually in reality, the issue is a little bit different than that. We are, whenever we trying to analyze one element, like the column, for example, like CA, we are going to find that it has under the lateral loads, if we are claiming there is wind load or an earthquake load, for example, and we have distribution of the lateral load as you can see here. So we are claiming that this element, the vertical element, which we call it column generally, it has two components, or there are two components are affecting on producing the straining actions. First one is related to the axial forces, whether it is tension or compression. In this case, we are going to have tension here because of the direction of the lateral load. And in the same time, this joint, in order to have equilibrium with the beam loading, then there is moment is going to be transferred to the column. And this amount of moment, it is not small so that we can neglect it. It's not negligible. This means that it is considerable amount of moment that we need to consider and take it into consideration whenever we are calculating the strength of the element. This brings us to the main concept of what we call it beam column. Beam column means that we are going to have straining actions that is going to combine both axial forces and in the same time moment. Both of them, they are going to contribute on the element, and the straining actions that is going to be developed are based on these two main components. Actually, this is going to be for the vertical elements, as we can see here, or it can be also for the horizontal elements like CD. If you look to this element, which is CD, you're going to find that it is going to resist the loads coming from the lateral loads here, which is P1 plus P2, because we have bracing here. And in the same time, there is moment going to be transferred, or there is moment going to be developed, at least because of the distributed load here. So we have a kind of moment here at point C. This means that this element, which usually we used to say that it is girder or beam, now it is going to be termed with beam column. So it is going to be termed with beam column. And this is the major difference between columns, beams, and beam columns. So before we were talking about columns only, we call them actually compression elements, where that only vertical loads or axial forces are going to be used or going to be existent, whether they are going to be compression or tension. So when they were tension, we called it tension member. When they were compression, we call them compression member. And when we used another element, horizontal element with distributed load, we called it girder. And this girder actually, it is going to have mainly flexural straining actions. But we said that it might happen there is small axial forces due to the friction or something or some restraint at the end supports, but we said these kind of axial forces are going to be neglected and they are not going to contribute to the main straining actions that is going to be developed in this element. And based on that, we said that it is going to be called beams, and officially we call it like flexural elements. So you like to call it beams, girders, anything. So it is flexural elements in general. But now we are going to talk about another type which is combining both, which is combining the axial forces and the bending moment at the same time, and we are going to call it beam column element. Okay. The relationship between the required and available strength may be expressed as usual, we are talking always about required and available. Required comes from the load combination in general, which is coming from the gravity load, wind load, earthquakes, and so on. So this is the coming from load combination. And here the available, which is how much strength that is going to be provided by the element itself, okay, whether in compression or axial forces or in flexure. So this is like actions, and this is, we can call it like the resistance. Okay, so whenever that we are going to have actions, or we are going to have required and available strengths, we need to compare them. Commonly, we want the available strengths to be larger than the required strengths. So we put this equation. And we said that required strength over available strengths should be less than or equal to 1. And we said that for compression members, we were talking about compression members before, we said that the strengths are axial forces only. For example, for LRFD, we mentioned about that before. This equation, we have explained about it before. It is P ultimate over phi c times Pn, the nominal strength, times the resistance factor. And here we are putting the ultimate load. It should be less than or equal to 1. So it was common for us to use this expression or this equation before. And for ASD, we mentioned similar equation, the actual load, or PA, over the nominal strengths, and this nominal strength is going to be, or we are going to use safety factor in the equation, and it is going to be less than, this should be always less than or equal to 1. These expressions can be written in a general form, so we can generalize the form, as we have explained before, to be in this general form, which is in the numerator we are going to call this PR to be the required axial strength, because we're talking about compression member, over the available axial strength. It should be always less than or equal to 1. Okay, less than or equal to 1. So this is what we can put it as a general form. So this means if we have one type of straining actions on the left, then we are going to put, relation between the required and available, then we are going to maintain this ratio within 1. That's the main idea here that we have explained many times before. Okay, now let's go and see the interaction formula that is going to be used in our case. Actually, the word interaction here, it is going to be related to what I have explained here. Okay, so we said in the axial member, we said PR over Pn should be always less than or equal to 1, right? This is the case of axials. But actually, if we're going to have beam column, as we have explained, we are going to have the interaction word here means that we have two types of straining actions. The first one is axial and the second is going to be flexural, right? So this means that the left-hand side here needs to have something that is going to represent the flexural part. So we need to add something here, like for example m, okay, over mn, for example, something like this, right? And it should be also less than 1, but the combination of the two. So from here we came up with the interaction formula for beam column. Then if more than one type of resistance is involved, take care of this word, resistance, okay, which means that axial resistance and moment resistance is involved. The interaction formula should be used where the sum of load to resistance ratio, which is the left-hand side that I have explained in the previous slide, must be limited to unity. It must be limited to unity. Okay, so this means that the required strength over available strength, this is going to be something related to axial force, as I said, and something related to flexural force. So this is axial and flexure. Okay. Okay, and it should be less than 1. If both bending and axial compression are acting, if we have bending and axial compression are acting, the interaction formula would be as we were expecting. Term for the axial force plus the term of the bending straining actions, or bending the ratios related between PR over PC, required axial strength, over the available axial strength, plus the required moment strength over the available moment strength. Both of them, the addition or the superposition of them, summation should be less than 1. Okay. As we said, this is MR. It is the required moment strength. If we're talking about LRFD, it will be ultimate moment. If we're talking about ASD, it is going to be the actual applied moment. And MC, it is the available strength. Okay, whether it is for LRFD, it will be phi b mn or phi b mn, okay, which is the resistance factor times the nominal strength. And if we're talking about ASD, it is going to be the nominal moment over the safety factor that is associated with flexure. Okay, and from here we can say that for biaxial bending, if we are commonly in the structure, we are having like two axes, X and Y, and if we are going to have two different types of bending moment around X-axis, for example, and Y-axis, this is going to be biaxial bending. In this case, the interaction equation, which is this formula, the moment term needs to be augmented to take into consideration the two different types of moments here. So in this case, we are going to have M related to X over MC X, so we call it MRX, the required moment related to X-axis, over the MC, which is the available moment strength related to the or around X-axis, and in a similar fashion we're going to put it around Y-axis. So the term that is related to the moment is going to be augmented, or going to be represented by two components, one related to X and another one related to Y, where this X and Y in this formula subscripts, this X and Y subscripts refer to bending moment, bending about the X and Y axes. So we are, as we said, it is around X and Y. Okay, so this is the meaning of what we are going to explain regarding the interaction equation or interaction formula, as we can see. So now we can put it in this form, or we can end up with this form. This is PR over PC plus the two components of moment, one component of x, one component of y. R means required strengths. C means available strengths. Okay. This equation is the basis for AISC formulas for members subject to bending plus axial compressive. Okay, if we're talking about flexural bending and axial compressive load. Okay. Two formulas are given in the specification. So we are going to use like variants of this equation and based on the axial force that is being applied. So if the element is going to have axial force, the P term or the axial force, if it's small, okay, if this P is going to be small, okay, we found that it's better, or of course it is based on the specification references. You can find the reason for this, and you can find that it is based on well-established research and experiments, that this formula for small axial load needs the axial load term, okay, needs to be reduced. Okay, so if P is small, okay, less than, for example, okay, 0.2, okay, this is related to the axial term, then we found that it is going to, in this case, we need to reduce the contribution of the axial term. But if this P is large, okay, we found that, which means that larger than 0.2, for example, this is the threshold that we need to take into consideration. So we found that this, if it's large, we found that we need to reduce the moment term slightly. It is not going to be reduced as here. Here we are going to reduce it by half, okay? But here we're going to reduce it by like by 1/9, which is 8/9 going to be multiplied here, as we're going to see now. Okay, so here the two formulas are given in the specification, one for small axial load and one for large axial load. Okay, if the axial load is small, if it's small, the axial load term is reduced. And for large axial load, the bending term is slightly reduced. So take care here. This is only reduced because we are going to reduce it significantly, actually. Half, almost. We are going to multiply by half. But for large axial load, the bending term is slightly reduced. Means that we're going to use 8/9. Okay? Only like 90%, around 90 or 89% of the bending term is going to be used. Okay. The ASIC requirements are given in chapter H. Okay, so it is all the details you can find in chapter H. Design of members for combined forces and torsion. You're going to find it in this chapter and are summarized as follows. We're going to see the summary of this. So we are going to have two cases here, as I have mentioned. One case for large axial load, another case is small axial load, and I highlighted it with the green highlighter here. So for PR over PC, larger than 0.2, we are going to have, this is the interaction equation that we are dealing with, which is PR over PC plus, take care of this factor, or this fraction here, this is 8/9, 8/9 the moment term. So this, what we call it, slightly reducing bending term. Slightly reducing bending term. This means that whenever that we are having large axial contribution, okay, this makes the component related to the axial force to be fully taken into consideration, and this makes the contribution of the moment in general to be a little bit less. Okay, that's the significance of, or the meaning here. Moment is going to be, or the effect of moment is going to be reduced by almost like 10%. However, on the other hand, if PR over PC is less than 0.2, we found that the effect of the axial force or the axial term is going to be not that much affecting. So we are going to reduce it by 2 here. That's the meaning of 2 here. Almost half of the contribution of axial force is going to be used. However, the moment term, it is going to be fully utilized. There is no 8 over 9 here. Okay, so that's the meaning of the two equations. Okay, this is the meaning of two equations. So remember, Will, if we have small axial loads, the reduced axial term is going to be reduced by 1/2. However, if we have large axial load, the axial force term is going to be taken into consideration, fully taken. However, that the moment is going to be reduced slightly by 10%. Okay. Whenever you see x and y here, as we said, x and y subscripts refer to bending about x and y axes. Okay, if we are having the element, this is x and this is y. So x, it is the strong axis, take care. Okay, x around the, or this is the strong axis. Okay. Okay, and we mentioned about this PR and PC before. PR required axial strength. PC, it is the available axial strength. MR required moment strength, as we said, M ultimate or MA based on LRFD or ASD. And MC, it is the available moment strength, okay, after using the resistance factor, phi b times Mn for LRFD, and Mn over the safety factor omega b for ASD. Okay, and this is what I have already explained in this two formulas. Here, two formulas are given in the specification, one for small axial load and one for large axial load. If the axial load is small, the axial load term is reduced. For large axial load, the bending term is slightly reduced. Okay, remember this. Okay, let's go to the next and like put it in what you can remember. Okay, and if you are going to use the slides as a reference for you, then you're going to find these are what you should remember always. Okay, I highlighted here the important things for you. So the remaining part is going to be like memorized easily for you. But here I put for LRFD and here ASD. So they are pretty the same. Okay, just we are, instead of in the denominator here, for talking about P ultimate and P or the axial force, in the LRFD we're going to use the resistance factor. So phi C here, phi B if we're talking about the bending. However, here in the ASD you're going to find the safety factor, which is omega C for axial forces and omega B bending for the moment terms. Okay. The threshold that you are going to use always is 0.2. So P ultimate over phi C Pn, if it's larger than or equal to 0.2, then you're going to use this equation, which is the force is going to be large, then no reduction for axial term, slight reduction for the bending term. If this P ultimate over phi C Pn is less than 0.2, then the opposite applies. We are going to reduce the axial term by 1/2 and letting the moment term to be the same. In a similar form, for ASD it is pretty the same. Also here, larger than or equal to 0.2, PA over PN over omega. If it's larger than 0.2, then we're going to use this interaction equation. And of course, we are talking about they should be less than 1. Less than 1 every aspect. So here we are going to have also 8/9 the moment term. The moment term here is going to be MA, which is the actual load around X, over MNX over this is the nominal strength around X, and this is the safety factor for bending, and MAY, actual loads or actual moment around Y-axis, the required one coming from the load combination, and this is MNY, which is the nominal moment around Y over or divided by the safety factor. Okay. Similar fashion, the same equation would apply here, but instead of 8/9 here, there is nothing here, it is 1, and here we are going to put 2. Okay, so it is the same. As I said, it is the same. Okay, this is what you should remember always whenever that you are dealing with the interaction equation, whether for LRFD or for ASD. Okay, and this is also, this is a kind of like another visualization for what we have said before. If we have like only one moment that is going to be there, if we are dealing with moment around the x-axis, which is the strong axis, for example, then we can use this equation. It is the same as I have said before. I'm not going to repeat it. Just you are going, the term here of the moment is going to be only one term. But if we are having two different moments around x and y, so we have term related to x, another term related to y, and in this means that we are going to have two terms inside the flexural part. Okay, two terms. Okay, and of course we are talking about two cases: larger than or equal to 0.2 or smaller than 0.2. Okay, so I think that now we are ready for having the example. We are ready to have an example after understanding or after like giving the idea of the interaction equation. Let's go to see an example here. Okay, so we have the beam column shown. This is the beam column, as you can see here. Okay, and this beam column is pinned at both ends. So we have pin here and we have another pin here, which is the end conditions. Okay, this is the end condition. So as I said, every word in the example, it has significance. Pinned here means that we are going to have, for example, k equal to 1. Okay, this means that our effective length is going to be 1. This is pinned at both ends and is subjected to the loads shown. So we have loads here, as you can see. P dead load 35 kips and P related to live load 99 kips. And as you can see, the length here is 17 feet, and at the middle we have concentrated lateral load QD and QL 5K and 12K. Okay. This is the geometry, end conditions, and the loading applied on this element. Okay, and we have the cross section is given for us, which is wide flange 10 by 49. Okay, and it is a 992 steel, means that it is F yield equal to 50 KSI. Okay, and the cross section, it is wide flange. This means that we are it is available for us to check the charts and so on for obtaining whatever the type of nominal strength that we are seeking. So now bending is about the strong axis. Take care of this point, because as I said, this is the strong axis XX. It has a significance. I'm going to show the significance of this word strong axis in the solution steps. This means that you can use the charts of beams, for example, directly without any problem. Okay, it's not around weak axis, it is around the strong axis. Okay, now determine whether this member satisfies the appropriate AISC specification interaction equation or not. So we need to know whether that the interaction equation is being fulfilled or not. This is the interaction equation. So as we said, we need to find, first of all, the solution strategy is going to be like this. We need to find this P ultimate, which is the required loading, and we need to find phi c times Pn, the nominal strength in axial compression, times phi c, and see whether that we're going to use this equation or this equation, which is larger than 0.2 or smaller than 0.2. This is number one. So we need to find this first. So the term related to the axial forces is important. We need to find it first. And after that, there is something we mentioned here. Strong axis means that we're going to use x only. This means that the second term, which is related to y, it is going to be cancelled out. It is going to be 0 because we do not have biaxial moment here. Okay, so this is the strategy of the solution: finding this term and then determining the equation that is going to be used, and then we're going to find the mn after that, and mr, which is the required moment. Already we know how to obtain the required moment from the applied load on the system. Okay, now let's go. So the first thing is, from the column load tables, the axial compressive design strengths of the wide flange 10 by 49 with F yield 50 ksi. This is, as we said, this is from the type of steel that we are using, A992, and an effective length ky times L equal to 17. As I said, ky here, it is 1 because we have both ends are penned, so we have 1 here. L, it is 17 already. It is from the previous, it is 17 feet as we mentioned before, as we said. Okay. Now we need to go to what? Column load tables. Do you remember this? several videos before I was explaining the details of how to use the column load table. So please revisit these videos and you can understand what I'm going to do now. Let's go to the load tables directly. Now let's check it. Here, this is for the column. You can go to the table 4-1, available strengths in axial compression, and this is in kips. We're talking about F yield 50, wide flanges, okay, and under W10, which is wide flange with this shape, okay, and with the weight that we are having. So wide flange, the shape is W10, and the weight per foot is 49 because our shape is 10 by 49, right? So this is the weight per unit length. Then we are here. We're going to find, we are talking about LRFD, right? Then we are going to choose here the KL with respect to the least radius of gyration, which is RY. We can find this is 17 here, okay? It is 17. 1 times 17, okay? This is the effective length. And then we can go for this one here and this one here. We can find 405. 405. This is what? This is the available strengths in axial compression for the element. Let's go back. Yes, it is 405 kips. Take care, it is phi c times Pn. Already the resistance factor is used here because we are talking here phi c Pn. Okay. So this is related to phi c Pn. Let's go back and see where that we are. We are here. We got this. The denominator is obtained now. Okay, now let's go to the next part, which is related to, let's go here. We want to get this part, okay, now in general, because it is x, whether that here or here, it is going to be used, so we need to obtain it first. Okay, since the bending is about strong axis, this is the significance of the word strong axis, as I mentioned before. The design moment, which is phi p, phi b, mn, for CB equal to 1 can be obtained from the beam design charts. As we said, design charts are accelerating the way or the solution for your problem. So you can visit this in part 3 of the manual, and you are going to find all the charts are related to CB equal to 1. Okay, but we do not know what is CB for our case, for our system. We're going to calculate it later, but now let's obtain this phi b mn based on CB equal to 1. So take care that we are talking about CB equal to 1. This can be obtained from the design charts or beam design charts in part 3 of the manual. For an unbraced length LB equal to 17 feet, let's go and see, check from the tables. This is the table from beam charts, table 3-10, wide shapes, wide flange shapes, available moment versus unbraced length. Take care here, we are having CB equal to 1. Remember, CB equal to 1. We're not talking about anything else. All charts, CB equal to 1. Then you are going to check the horizontal axis, which is unbraced length, as you can see it here, until you find, yes, here 17. So 17, the unbraced length that we have. Go up until you touch with this dotted line, which is our shape. Our shape is wide flange 10 by 49. So this is our shape. This is the shape that we are having. Then if you go up and hit the line, the dashed line, and go horizontally, you're going to find here we are between these two values, these marks, and we found it 197. 197. Let's go back and put it as we found it. Yes, it is 197. For the end conditions and loading of this problem, CB equal to 1.32. Who says that? Let's assume that our case, what is our case? Now let's go back. This is our case. We are having pin condition. This is the boundary conditions. And we have concentrated load at the middle, right? So let's revisit. This can be obtained from figure 5.15c. Okay, let's see this. Okay, which is, this is in the text, this 5-15 something, this is the textbook, but you're going to find it in the design of flexure members, the manual. We're going to find table 3-1 values for CB for simply supported beams. This is our case. Concentrated load, and we have like bend in condition here. So lateral bracing along the span, none, and we have something here. Do you remember the supports here with crossing? This is going to give us 1.3. So CB is going to be 1.32. Let's go back and deal with this. So CB equal to 1.32. Now, as we know, this is the load for, or this is the strength, available strength for CB equal to 1. But we have CB equal to 1.32. CB is going to contribute to enhancing the available strength of the section because it takes into consideration the moment gradient. So we are going to increase the available strength by almost 32%. Can you imagine? So it was 197. Then we're going to multiply it by 1.32. We are going to obtain 260. But there is something here. This supposedly to be the available strength. But under one condition, it should not be larger than exactly phi b m plastic, the plastic moment, the plastic limit. Do you remember when I was talking before? Said that we have two things here like this. This is the unbraced length, and this is m here. And I said that this is the limit for the plastic limit. Okay, this is the m plastic here. So if we are, for example, we are here, and then we multiply it by CB, and we found that we are here for this cross section, this cannot be done. We have limit here, which is MP, right? The plastic limit. The section would not reach this limit. It would yield before reaching the amount that we are talking about here. This moment is larger than phi b MP, which is 226.5 foot kips. From where we got this? Exactly. If you go back to the beams, for the same dashed line here, we're going to find the horizontal line, okay, for our section. Look to it, you're going to find it exactly 226.5. This is the plastic limit, phi p. Okay, this is the plastic limit. Okay, so this means that, can go back. Okay, take care of this because really it is very important for us. Okay, so also obtained from the beam design charts. So the design moment must be limited to this limit, which is the plastic limit. As I said, we have this. This is the plastic limit that we need to limit our cross section for. Therefore, phi b mn equal to 226.5 foot kips. Okay, this is considered the limit for us. This is the available moment strength. So now we got from here one, which is going to be the term for axial load. This is the nominal strength or available strength for axial load. Here, this is number 2, which is the available strength for flexural behavior or for the moment term, right? So now we have these two terms in our hands. Let's go and see how we can apply the interaction equation. Okay. So before that, our interaction equation needs, if you remember, needs the required factored load. Okay, so let's go back and see here what we were talking about. So this is the interaction equation, for example, but we need to get P ultimate at the first place to see whether that we are here or we are here, right? So we need to obtain the ultimate axial force, the ultimate axial force. So here, this is the ultimate. We need to get it from the factored load. Remember, this is the loading condition of our problem. This is the loading condition of our problem. P ultimate equal to 1.2 plus 1.6 life. 1.2 dead plus 1.26 life. It is gravity loading here. Remember, everything, it is gravity loading. Dead load and live load. Dead load and live load. Okay, so it is going to be the controlling load combination here. So we have this 1.2 times 35 and 1.699 here. This is the axial force. And for the lateral force dead and live also, it is going to be 1.25 plus 1.612 given here. So we have 225. So the maximum bending moment occurs at mid height. Okay, so we know now P ultimate. Okay, so P ultimate, we are going to use it for the obtaining the threshold, and the other Q ultimate is going to be used for obtaining the M ultimate, which is the ultimate flexural moment, right? Because this is the term that is going to give us the moment, which is going to be maximum moment here, if we say something like this. Right? So this is the maximum moment here. This is the M ultimate. PL over 4. Okay, this is P, which is the horizontal concentrated load, times L, which is the height, over 4. Okay, this is the formula for maximum bending moment. It gives us 107.1 foot kips. Right? Now, let's go and determine which interaction equation that is going to control. Which interaction equation that is going to control. So first of all, we're going to find that P ultimate over phi c Pn is going to be 200.4 over 405. This is P ultimate. Already we have obtained it from here. This is the ultimate axial force. And phi c Pn equals to 405, which is already we have obtained it from the previous here, right? This is number 1 related to the axial force, the maximum axial force, right? So we are in the right track now. So we are having this ratio. We found it, this ratio 0.49. It is larger than 0.2. This means that we need to use the equation. Which equation here? The axial term is very large or larger than 0.2. The equation here that we should use, the equation that is going to have slightly reduced bending moment term. So the axial force is going to be represented as it is. This is the axial term. As it is going to be represented, as you can see here. However, the bending term is going to have 8/9 slightly reduced. Okay, so it is going to be, this is the interaction equation that we're going to use, P ultimate over phi c Pn, which is 200.4 over 405, plus the term that is related to the axial, the moment. We know that this term is going to be cancelled because we have, this is 0, because this term is no moment here around y. We used only strong axis, right? So this term is going to be cancelled. And then the remaining term is going to be this term, 8/9. Okay, so 8/9. M ultimate, already we have obtained it from here, 107.1. And the maximum 226.5. It is already obtained from the previous slide, as I have said. This is, remember, this is the M plastic, phi b, M plastic, okay? The limit of the section. This means that, what is the meaning of this? This means that if this cross section is going to fail, it is going to fail by yielding. I mean that by reaching M plastic, more than yielding even, okay? This is M plastic. Okay, this is the contribution that we're going to find. When we put both together, okay, we're going to find that it reaches 0.9. Still, it is less than 1. This means that our cross section is working well. Our cross section is working well, and we can say that this member satisfies AISC specification, which is W10 by 49. Okay, W10 by 49. Okay, this is going to be the term, or this is going to be the equation, and this section is satisfying the requirements for the interaction equation according to AISC. Okay, so this brings us to the end of this this video. I'm going to recap what I have said. I hope that it is clear for you. The important thing I want you to remember that we have beam column, which means that it has axial and compression, compression force and flexural components working together. And then we mentioned about there is an interaction formula that we need to take into consideration, which is going to have the required strength over available strengths going to be, the ratio between them should be less than 1. This is if we are having more than one type of resistance. AISC make it easy for us and said that this is going to be our interaction equation, which is term for axial compression, another term for axial for bending, and it is going to be two terms, one around x, one around y. And we said that we have like two cases, one case for small axial force, another one for large axial force. Okay, and then we put it in this way. We said that we have one case which is large axial load. We are going to slightly reduce the contribution of the moment term, and if the second case apply where that PR over PC is less than 0.2, the case of small axial load, then we are going to reduce the contribution of axial force by half. So we are going to reduce the axial term. And after that, this is what we have obtained, and this is how, this is the two equations in AISC that we're going to use for the interaction equation. And after that, we like summarized for LRFD and ASD. They are pretty the same, only you need to check whether your axial load is larger than or equal to 0.2 or less than, and then use the appropriate interaction equation. After that, we ended with example that is giving to us application for what we have done. The important thing in this example that we have concentrated load at the middle and we have pinned conditions. And this makes it easy for us to get the important terms in our equation. We need phi CPN, which is related to the axial term. We need to obtain it first, and then we need to obtain the phi BMN, which is the available strengths, moment strengths for our section, which is the second important term here. And then we use the column charts, beam charts, and we used the actual value of CB. Okay, take care of it because it really increases the available moment strength by 30% in our case here. And then we substituted in the equation, and we found that our interaction equation is 0.9, which is almost okay for this cross section. Okay, thank you for listening, and see you in the next video.